written the access. So okay. Yeah, feel free to take your papers from last time. So yesterday was yeah, good afternoon, guys. Yesterday was the due date for ROC 3. So I want to make some comments. And so in homework 2, there was a question why the scaling helps for k-nearest neighbors. And I saw some students replied that it helps for convergence, but it's absolutely irrelevant because for it's important for convergence in gradient descent, but not in k-nearest neighbors. In k-nearest neighbors, when we calculate the distance, we take the sum over all features, and if some features are not in one scale, then they will have more kind of importance. So this is the idea behind why the scale helped in k-nearest neighbors. So in homework 3, the first class was a very large class, gradient descent. If you didn't implement regularization, it's fine. We will take only 1 point off. If you implement regularization, but only for one of the methods, we will take only half point, because in the end of the day, you will use built-in gradient descent, not your implementation. I just wanted you to understand all the parameters that built-in algorithms have. So then you were supposed to apply this for unscaled data and observe that it doesn't converge for some parameters, then on scaled data, and observe that it converges. And then I asked to make some kind of to make some analysis. And this what you could come up. So first, small learning rate helps for convergence. And this is expected because if you I will draw this again. If you have unscaled loss function, then it can be stretched along one feature dimension. So this is point of view from above. These are the level curves for paraboloid. So our paraboloid looks like that. And these are the lines with a constant value of the loss function. And for scaled features, it's more symmetric. gradient is always perpendicular to the constant level curve. So its next step, the gradient will go like that, perpendicular to this level curve. And if it's large, then you will end up at the point with high value for loss function. But if you multiply by learning rate, you will end up somewhere closer. So if you just scale this vector. So that's why the small learning rate always helps for convergence. But there might be an issue with small learning rate that if you use a really small learning rate, then the update steps will be very small, and you will need to perform. So next gradient is perpendicular to this line. The next gradient should be perpendicular to this line. So you may need to make a lot of steps. And this is actually that you could also observe in your homework. Like for a small learning rate, the error term was pretty large because we need to do more iterations. For example, for 1,000 iterations, this number is a little bit smaller, but still pretty large. So maybe you should perform not 1,000, but 10,000 iterations. So, but if you increase learning rate, like here, then you will converge faster. The other problem with scaling is that if you look at the gradient for scaled version, and you will go in the direction perpendicular, then you will end up much closer to the minimum than for unscaled loss function. So this is another reason why we want to scale our features for gradient descent. So another observation, the batch size. In our data, but also it's typically general case for batch size 1, which is called stochastic gradient descent, the convergence, so this number is 4435, and for larger batch, okay, it's also 4435, but here is larger. The smallest one, 4433. You get the small error actually just for stochastic gradient descent. And it's an interesting observation because when we use full batch gradient descent, the trajectory is a straight line to the minimum. But yeah, and in stochastic gradient descent, the trajectory is noisy. But it turns out that with smaller batch size, your algorithm will converge faster than with full batch size. So that's why in practice, the stochastic gradient descent is used not only when your data doesn't fit the memory, but just because it results in better convergence. Okay, that's finally, after that, not finally. The second part of the homework was to choose the features, important features, and you could just run through all possible combinations, like one feature, two features, and maximum number of features. But in the interest of time, you could draw, in this case, I drew the mutual information for different number of features. And of course, the best accuracy is here, but we don't want to use all the features. So we can look at the number of features in this range, which is about 30. You could use another approach, recursive feature elimination. It also results somewhere around 30. And finally, you could run a grid search. And instead of going through all possible numbers from 1 to the maximum number of features, we can just, to make faster, to iterate through the range around 30. And after that, in my case, the best number of features was 27. And finally, we report the score on test. You could report R-squared because it's standard in statistics. You could report mean average error because it has clear interpretation, just the deviation of prediction from true value. You could use MSE and justify this because it's standard metric in machine learning, but it's maybe better to use RMSE to use the same units. Yeah, so this is what I expected from you for homework 3. So this was model selection and feature selection for classification, for regression. Today, with this week, we will talk about model selection for classification task. Oh, I didn't pass the paper, so
Is this solution going to be posted anywhere?
okay, yeah, I will upload this on my courses. So this homework was under week 4, so I will upload solutions there.
The extras.
Okay, and did you take the last one from last class?
Oh yeah, I've got these. I
Okay.
just, those are the extra papers.
Thank you.
So,
So, last week we talked about precision and recall. Let me open these problems. Yeah, don't forget to write your name on the paper. So last time we talked about precision, recall, and F1 score. But those metrics we calculated for fixed thresholds. Now we want to evaluate the model, and for this task, we will use so-called precision recall curve. So we will calculate precision and recall for all possible thresholds. As you remember, when we talk about linear classifier, the decision boundary had equation, this linear function equals 0 with extended vector x by 1. And for a point outside, if we draw a line through this point, the equation has this form wx equals some different number, alpha. So, and we can actually then classify our points. We can choose some threshold and classify points based on this dot product between w and x. If this dot product is greater some threshold, we will assign positive class. If smaller, we will assign negative class. So in this table, you can see this algorithm prediction A of x, which is just a dot product. And the first step will be to sort these points by this dot product. So A of x, true prediction, the algorithm prediction, and the first value will be 2. The true label is 1. Then 0.7. So we kind of sort our points by the algorithm prediction. Then 0.45. The label is 1. 0.3. The label is 1. 0. The label is 1. Negative 0.1. The label is negative. And finally, negative 0.5, label is negative. And to get the predictions, we should choose a threshold. So for example, if I choose a threshold like greater than 0.5, then all the points will like above with algorithm value above this threshold, we will classify as positive class, like 1, 1. I don't want to write this because we will go for all possible thresholds, but I just want you to understand that when we choose threshold, the prediction will be positive for values A above this threshold and negative for values A small. Okay, so let's choose, so precision recall curve. We should plot precision and recall. So we should calculate precision and recall. And let's choose our first threshold like greater than 2. This will be threshold 1. So if you look at the formula for precision and recall, in numerator we have true positives. How many true positives do we have for the first threshold? In other words, how many points our algorithm will predict as one? No, zero. Zero, because greater than 2, we don't have points with a greater than 2. Does it make sense? So for the first threshold, both and this fraction will be 0. This will be our first point on this plot. Then we choose the second threshold, like everything that greater 0.7. Now, how many true positives will we have if we use threshold greater than 0.7? So this point now will be classified as 1. And all other points will be classified as -1. So now true positives will be 1 number of true positives. I hope you agree with that. Okay, so numerator for both fractions will be 1. Let's think about denominator. For recall, it's the total number of positives. So what will be the total number of positives? How many ones do we have in this column? So these are true values. 4. So recall will be 1 over 4, 1/4. Precision. Precision in denominator. So, and by the way, for recall, denominator will be 4 everywhere. In the entire column, denominator will be always 4. For precision, denominator is the number of points that our model predicted as positive. So what is the number of positive predictions for our threshold 2? 1. So the fraction will be 1 because the number of true positives is 1 and the total number of points that our model with threshold 2 predicted as positive is also 1. So this is our second point. 1/4 for recall and 1 for precision. Threshold 2. Okay, then we choose next threshold here, like greater than 0.45 or 0.5. Now our model will classify 2 points as positive. But how many true positives will be in this case? 1, because the second will be actually false positive. 1. So that's why the recall will be again 1 over 4, because the true positives is 1 and the number of total positives is unchanged. Precision, it's true positives 1 over total number of points predicted as positive. In this case, it's 2. So this is next point, 1/4 and 1/2. And let's do one more, and I will ask you to continue. So for next threshold, like greater than 0.3, So if you have any questions, please stop me and ask. So for next threshold, we have 3 points classified as positive. And how many true positives will we have for this threshold? 2. So recall will be 2/4, but precision will be 2/3. And as you can notice, in precision denominator, when we decrease our threshold, denominator always increased by 1. In precision, denominator always will increase by 1 because we have more points that our model classifies as positive. That makes sense? So let's draw this point. 1/2 and 2/3. So 4 blocks stands for 1/3. This will be threshold 4. And I will ask you to continue now this plot. In the end, we will connect these points, and the resulted curve is called precision recall curve. So please continue this plot. I will continue with you, but in Python, because in the homework I won't ask you to plot manually this plot for 1,000 points. Of course, we will call it built-in function. Don't remember the comment, but we will use these comments next week, so I will look at these functions here. Okay, so these are our data. We could sort them. So yeah, so I've sorted the data by the output from the model. And now we should choose the threshold. So for example, greater than 0.7, and you will get this predictions from the model. Everything that is above will be positive, everything that below will be negative. But to get this in numbers, 1 and -1, I will multiply by 2 and subtract 1. Yeah, so for this threshold, this vector represents the predictions. So I will call this y-pred. And now we can calculate, for example, precision score, and recall score between true values and y-pred. And as you remember, our second point was actually 1/4 and 1. So recall was 1/4 and precision was 1. But we want to calculate this precision and recall for all possible thresholds. So for this purpose, we can use precision recall curve. And it actually doesn't matter if you apply this to the sorted arrays or unsorted. Let's see, it's because under hood it will actually sort by A. So we need precision and recall. So these are numbers that you should have in your table. Like for recall, it's 0, then 1/4, 1/4, 1/2, and so on. For recall, there is only one difference. It counts 0 over 0 as 1. So you can leave 0 in your table, but then it will be 1, 1/2, 2/3, and so on. So if I would use unsorted data, the result would be the same, because under the hood, this function would sort the data. And now we can plot it. Recall and precision. And this is how your plot should look like. Except the first point, the first line will go from 0. Second one, it begins from 1, but this is the only one. So this is the first point with coordinates 1/4 and 1. This is the second with 1/4 and 1/2. Here will be 1/2. So you should get some something that looks like that. And the last three points, they will have recall 1 for all these points. But precision will drop because we will have more incorrectly classified points. Okay. Do you have any questions? Yep. Where? Sorry. Oh, yes, sure. Yep. Now we will go back, but actually, okay, but I can wait a little bit. So, yeah, so when we choose the last threshold, like a very large negative number, then all the points will be classified as positive. It means that recall will be 1 because the number of true positives will be the same as the number of total positives. Recall will be 1. But precision will be the number of true positives, which is 4, over total number of points. So it will be 4 over 7, the last precision. The previous will be 4 over 6. Okay, so what if our model would predict, would return numbers, a little bit different numbers? For example, for this point, it would predict a low number so that we had only once before some threshold and then on the negative ones. So let's look at this case. So I will make this number positive. And look at the precision of PR curve in this case. So if our model kind of predicts everything correctly, then the PR curve looks like this square. And what is the area under this curve for the perfect model? Wow, yeah, it's just unit square. And now you can actually understand why people use this metric. For perfect model, area under this PR curve equals 1. For like our original model that that after sorting the points based on the prediction had some alternations in the predictions. It doesn't have area 1. And also it's not monotonous function. So that's why typically people are using the second metric, which is called area under the curve. And the curve is called receiver operating curve. So again, it was proposed in 1940s during World War II in radar signals. So that's why it has this weird name, receiver operating curve. But it's the most common metric for classification. So let's look at this second metric. This should be problem one. So it has the true positive over total number of positive, and it's called true positive rate, but it's exactly the same as recall. So at least one column we don't need to calculate again. So the second axis is different. It's called false positive rate, and this is the ratio of false positive prediction to the total number of negative points. So let's add this extra column to our table, false positive rate. And calculate, so this is the number of false positive over total number of negative points. So let's calculate for the first threshold. For the first threshold, do we have any positive predictions at all? For the first threshold, greater than 2. We don't have any positive, neither for true positive nor false positive. So it will be 0. It will be 0. And the first point for this plot will be again at the origin. And it will be at the origin also in scikit-learn. So the second threshold, everything greater than 0.7. What is the number of false positives for this second threshold? What is the number of the number of true positives is 1 because the true label is 1. What is the number of false positives for the second threshold? 0, 0, yes, 0. So the next point will be 0 and 1/4. 0 and 1/4. So this will be the second point. Threshold 2. Then we choose threshold 3. Then what will be the number of false positives for threshold 3? What is the number of false positive for threshold 3? How many points our model, how many negative points our model classified as positive? 1, just 1. So for the false positive rate, we will write 1, the number of false positive, over total number of negative. Total number of negative is 3, 1/3. So next point will be 1/3, 1/4. 1/3, 1/4. So this is threshold 3. And you can notice even now these this the word well, that every time when our model doesn't make a mistake, we go up. When our model makes a mistake, like in this case, it made a mistake, we increase the false positive rate. So next point, let's calculate next point for threshold 4. What will be the number of false positives? it will be 1. Yeah, for this threshold, it only one false positive. So, and because our model didn't make a mistake, the false positive rate will be unchanged, but the true positive rate will increase 1/2. So it will be 1/3 and 1/2 here. So we kind of go up for threshold 4. And now you can actually guess how it will look like, because then we have we will have two correct predictions when we lower our threshold. So it will go up 2 times, and then we will get 2 incorrect predictions. So we'll go to the right 2 times. So we will go up twice, and then we will go to the right twice. So the final plot should look like this, but I ask you to calculate to continue this table. Meanwhile, I will do this in the Python. Display. Yeah, so in Python, we call this function ROC curve display, and it will plot this curve, and also it will calculate the area under this curve. And in your paper, you can also calculate this area will be 1/12. This area, the height is 1, the length is 2/3. It will be 2/3. 2/3 is multiplied by 4, 8, 12. So the total area will be 9/12, and you can cancel by 3. You will get 3/4, which is 0.75. So yeah, did you plot this second? Okay. So let's think about what is the best value for this AUC area under the curve, and the worst case. In the best case, if our model doesn't make a mistake, then we will always increase the true positive rate and then go to the point with coordinates 1, 1. So what will be the area for the perfect model? 1, 1. What is the worst model? The worst model always alternates the predictions, like every time it makes a mistake. So the worst model will go like stepwise. What will be the area for this model? 1/2. If you think about like many points, much more than 7, then the steps will actually look like a straight line, like diagonal. 1/2. So this is the first metric that we use, which is not between 0 and 1, but between 1/2 and 1. So the worst case is 1/2, and the best case is 1. And you can see from the plot that this function is always increasing. So it doesn't have these dips like PR curve. So that's why typically this function is used in practice. But it's not the perfect metric. I will show you the situation when the area under the curve of this receiver operating curve is almost 1, but the model is bad. Well, let's look at this example, and then we will go to the second part of our lecture, Perceptron algorithm. So here is this example. Consider this case that the number of points is 1 million, and our model predicts the majority of points, like 900,000, like with small value of dot product, then 100 points with positive labels, and then the rest points with negative labels with high dot product value. If you look at the threshold somewhere here, then what can you say about recall? Recall is the total number of true positives over total number of positives. So what will be recall for this threshold? What is the number of true positives? It will be 100. So recall will be 1. Recall will be 1. If you look at this threshold, recall will be how many true positives? 0. So this is the plot of this ROC curve. So it's 0 for 500 for 50,000. Then it's 1. And then it stays 1 for all other objects. So the area is 95%. But the area is good. What about the model? What do you think? Can we use this model for prediction? Maybe not, because 50,000 objects it classifies incorrectly. So this is an example when area under the curve for RT dot curve, but precision recall curve area is 0. So sometimes we use both metrics. But this is a very rare case. If you look at the data, you will notice that this is highly unbalanced data. And as you remember from week 2, for unbalanced data, we can't apply even accuracy as the metric. So it's kind of extreme case. Okay, let's move to our next topic for today. Rosenblatt's perceptron. So this is the linear classification algorithm. So we know linear regression, we know logistic regression. This is another one. linear classification, which is called Perceptron. And it was proposed in 1960s, and I took the illustrations from a nice textbook by Bishop, a little bit outdated, but they have the second, he and his son wrote last year a second volume of this textbook that includes the So I just want to show you how the weights were updated at that time. It was an electric circuit, and the weights were updated by 1 or -1. So today you will see that you can write this amount of code to implement this algorithm. At that time, it took the entire machine to update the weights. So let's look at our loss function. Loss function, when our model, if we assume the threshold is 0, then the sign of A actually will represent the class, one or less. So if the sign is positive and the true label is positive, this value, this expression will be false, and the Einstein bracket will result in 0. But if they're different, then it will be true, and this sum actually represents 1 minus accuracy or error. And last time we proved that for incorrect classification, the margin is negative. So it's exactly the same as calculate how many points we have with negative margin. There is one misprint. Sorry, disregard this. So if we want to minimize the error, and the error is this, we can represent an error as the sum of negative margins. So we can take the sum over all the incorrectly classified points. Actually, why we can use the first line? Because it's not differentiable. So if we rewrite the first line as the problem where we want to maximize the margin, the negative margin, because negative corresponds to incorrect classification, then it's a nice linear function and we can take a derivative. And that's it. So this is the entire algorithm. We apply stochastic gradient descent. So we take arbitrary point. If the point was incorrectly classified, we update our weights. This is the gradient of the marking, y times x with respect to w. If the point was correctly classified, we just keep it and continue iterations. So let's look at the result. So this is notebook 11. So it's a very simple algorithm, as you can see. So this is our data set. This is our code. Just if one is negative, we update weights. Otherwise, we continue iterations. Okay, let's. It's almost done. Okay. Okay, so we initialize weights randomly. So this blue line is initialized somehow. Then we take arbitrary point. And if this point, red point, was incorrectly classified, we make one step. Hop. And it's hard to see, but this is our blue line. It's kind of rotated to take care of this misclassification. Then it takes another point and updates the weights. Then it will update the weights according to this point. So now this point is correctly classified, and we continue this process. So let's talk a little bit about geometry. The black vector represents the W, the normal vector to our decision boundary. The red vector is the vector from origin to our point S. And as you remember, the algorithm was W minus gradient, and gradient was just Y, and Y is 1 or -1 times X. So we just add X. So the new vector W, is the result of summation of this black vector W and X. So this is the sum. So we have a new vector W, and then we can plot a line perpendicular to this vector. And this is all out. Then we take a new point, subtract W and X, and we get a new vector W. Let's look at the example for separable data, when we can actually separate our points. So this is the original position of our line. This is a random point which is misclassified. And now I will run our algorithm, and I want you to be very attentive, and because it's really exciting to watch the algorithm for separable case. Okay, 1, 2, 3. Once more. We will make one iteration and we're done. So there is theorem that for separable case, this Perceptron algorithm always converges, and you can see that it can converge even in one step, in one iteration. For unseparable case, it always will have some misclassified points, so it will kind of oscillate about the correct decision boundary. Yeah, I think we can stop here for today. I just want to maybe emphasize that for different algorithms like linear regression, logistic regression, perceptron, we will always get a little bit different weights. So the position of decision boundary will be a little bit different for different algorithms, because we maximize different objective functions. So next time we will talk about support vector machine, and that will be our last classification algorithm. Okay, so yeah, bring your papers. Let's clean this up.